Welcome to the Dup Dive, the show where we take complex topics and really try to break them down into their most digestible, fascinating parts.
Glad to be here.
Today, we're plunging into the world of automotive functional safety. It's a topic that's become, well, not just important, but absolutely paramount, wouldn't you say?
Oh, absolutely. Non-negotiable these days.
Yeah, think about it. Modern road vehicles, they're not just mechanical marvels anymore. They're these intricate software-defined machines just packed with complex electrical and electronic or E-systems.
Everything from 80s to engine control.
Exactly. And this escalating complexity, it isn't just about cool new tech. It means designing for safety proactively is, well, it's essential for protecting lives and property on our roads.
You've hit on the core challenge there.
Yeah.
And that's precisely where ISO26262 comes in. It's the international standard, the benchmark, really, for functional safety specifically in road vehicles.
Right. And today, we're doing a deep dive into a very specific, but you're saying vital, piece of this puzzle.
That's right. ISO26262.2019, Part 8, which is titled Supporting Processes.
Okay, supporting processes. Sounds maybe a little dry compared to, I don't know, talking about specific safety features, but you're telling me it's more fundamental than that. It's not just what needs to be safe, but the how.
That's it, exactly. You see, while other parts of ISO 26262 define what needs to be safe, the safety goals, the design principles, the verification activities, Part 8 focuses entirely on how that safety is systematically achieved. And then, just as importantly, how it's meticulously maintained throughout the entire lifespan of the vehicle and its components.
Oh, okay.
So these supporting processes, they aren't just independent stages you tick off a list. Not at all. They are the foundational, continuous activities that ensure all your functional safety efforts are systematic, controlled, transparent, and, ideally, highly efficient.
So they're kind of running in the background all the time.
Exactly. Think of them as the unseen but utterly crucial infrastructure. They make the entire safety development and operational journey robust and reliable. They're the backbone, really, that keeps everything else standing. Without them, you might have great ideas for safety, but frankly, no reliable way to execute or prove them.
Okay, that paints a much clearer picture. So they're not merely steps in a sequence, but more like the overarching principles and practices that underpin everything. What's the broader context for Part 8 within the whole ISO 26262 standard? Where does it fit?
That's a great starting point. To truly grasp Part 8, you first need to understand the broader context of ISO 26262 itself. Now, this standard is in essence an adaptation of an even broader international standard, IEC 61508.
Right, the General Functional Safety Standard.
Exactly. But 26262 has been specifically tailored for the unique and, let's face it, highly dynamic world of E-systems in road vehicles. And what's critical to remember is that functional safety isn't achieved by looking at one component in isolation or, by focusing only on the final product.
It's got to be holistic.
It has to be. It's about a holistic approach, incorporating safety measures throughout the entire safety lifecycle.
Mm-hmm.
And that lifecycle is extensive. It spans everything from the initial development phases through production, ongoing operation, servicing, and even the eventual decommissioning of a vehicle.
So it's really about building safety in from the absolute ground up and then continuing to manage it. This isn't a one-and-done kind of thing at all.
Precisely. You can't just design it safe and walk away. And Part 8 is absolutely central to that continuous management. It specifies the essential requirements for these supporting processes. These processes aren't optional extras. They permeate every single stage and aspect of functional safety development.
Okay.
To use an analogy, if you think about the V model, which is a core reference process model in the ISO 26262 series, showing development and testing phases mirroring each other.
Right, the V shape showing requirements down one side and testing up the other.
Exactly that V. If that represents the core path of product development, then these supporting processes in Part 8 are like the scaffolding that surrounds it. They're the communication channels connecting every team and the quality checks that enable and validate every single step within that V model. They ensure consistency, traceability, and the overall integrity of the safety argument you're building.
I see. So they're not the individual building blocks of safety themselves, but maybe more like the mortar holding the blocks together, the framework, the quality assurance.
That's a great way to put it, the mortar, the framework, the QA. The core message here is pretty profound, actually. Functional safety isn't merely about the final product's characteristics, whether the airbag deploys on time or the brakes engage correctly. It is deeply, inextricably embedded in how that product is conceived, designed, implemented, manufactured, and managed throughout its entire lifespan.
Right, the how is key.
It is. These supporting processes provide the assurance that safety by design is truly achieved and critically maintained. They give you the confidence, the evidence, that the product remains safe as it evolves, as components inevitably change, and as it operates out there in the real world. Without them, even the most brilliant safety concepts can just fall apart in execution or over time.
That makes a lot more sense. It's really about the underlying system for creating safe systems. Okay, let's dive into some of the key management supporting processes outlined in Part 8 then. First up, Clause 5, interfaces within distributed developments. Now, in today's globalized auto industry, with seemingly countless suppliers and partners, I imagine this is absolutely crucial.
It's not just crucial, it can be a minefield if not handled meticulously. This clause, Clause 5, aims to clearly define the interactions and dependencies that inevitably arise when development activities are distributed. Between a customer, say, a big vehicle manufacturer, an OEM, and their various suppliers. It's about meticulously describing the allocation of responsibilities for safety-related tasks, and precisely identifying and managing the work products, the documents, the data that must be exchanged between all parties involved.
So the goal is no pointing fingers later. Everyone knows exactly what their part is.
Exactly. No ambiguity. The fundamental concept here is that functional safety in distributed development is a joint responsibility. Both the customer and all the suppliers involved must comply with ISO26262 requirements. It's not enough for just one party to be compliant.
Right, the whole chain has to be strong.
Precisely. And crucially, these responsibilities are agreed upon across all safety lifecycle phases, from the initial concept and development right through production, operations, service, and eventual decommissioning. This comprehensive view ensures no gaps are left open anywhere along the line.
This sounds like it could get very complicated very quickly, especially with complex global supply chains. How do they formalize all this? Is there a specific document?
There is, and it's vital. That's where the Development Interface Agreement, or DIA, comes in. This is truly the cornerstone document for formalizing these complex relationships. It defines the roles, the responsibilities, and ensures everyone has aligned safety planning.
The DIA? Okay.
I've heard it described this way. The true genius of the DIA isn't just about listing shared tasks. It's forcing companies to have the difficult divorce agreement conversation before the marriage even begins. You explicitly define safety responsibilities up front.
That's a powerful way to put it. Avoids costly finger-pointing down the line when inevitably something goes wrong.
Exactly. It forces clarity.
So what are some of the non-negotiable elements that have to be in a DIA according to the standard?
Okay, the standard, specifically 5.4.3.1, is quite detailed.
Right.
A DIA must, at a minimum, include the appointment of dedicated safety managers from both the customer and supplier sides. Clear points of contact.
Okay, named individuals.
Yes. It needs to cover the joint tailoring of safety activities, how you adapt the standard for this specific project. A clear delineation of which safety lifecycle activities each party customer versus supplier will perform. This includes joint planning for things like functional safety assessments and audits.
Right. Who does what?
Then there's the detailed specification of information and work products to be shared, including all the necessary documentation for building the safety cases. You need to know what you're exchanging and when.
So even the specific paperwork is spelled out.
Absolutely. Yeah. The DIA also assigns clear responsibility for each safety activity, often using RACI definitions. Who is responsible, accountable, consulted, informed. Very clear roles.
Ah, the RACI chart. Classic.
It works. It also requires confirmation of target values for hardware architectural metrics, things like the single-point fault metric and the latent fault metric. This ensures everyone's aiming for the same hardware safety target.
Gotcha. Consistent targets.
They also need to agree on interface-related processes, methods, and tools, including their specific versions and configurations, to ensure seamless collaboration. You can't have one team using version 1.0 of a tool and another using 3.0.
Yeah, that sounds like a recipe for disaster.
It can be, and a big one. Determining who performs safety validation, especially considering that full vehicle integration is often needed for proper validation. Who's responsible for that final check?
Right, because the supplier might not have access to the whole vehicle.
Exactly. And lastly, there's planning for the supplier's functional safety assessment reports, their contents, versions, milestones, and importantly, an agreement allowing customer-assigned auditors to conduct functional safety audits at the supplier's premises. That transparency is critical for building trust.
That makes sense. You need the right to check up on things. And once that agreement is in place, how is it managed on an ongoing basis? It's not just a document you sign and file away, right?
No, not at all. It's a living agreement. The standard 5.4.4 talks about execution. The customer has a role in ensuring timely information exchange. The supplier is responsible for reporting any issues that could increase risk or any safety anomalies they find, including those originating from their own subcontractors, their Tier 2s.
So it flows down the chain.
It has to. Identified safety anomalies must be analyzed and resolved with clear agreement on who takes action. The supplier also needs to confirm the feasibility of the customer's safety requirements and communicate back if they see any need for additional safety requirements from their side.
Okay, a two-way street.
Definitely. And of course, consistent progress reporting against the agreed safety plan milestones is a must. It's a continuous conversation and collaboration managed through these defined interfaces.
And what happens after development wraps up? When things move into production and operation, is that covered too?
Yes, Section 5.4.6 addresses the post-development agreement. The supplier provides evidence that their production process capability meets the requirements of ISO26262, specifically Parts 2 and 7. Then, a separate supply agreement typically defines responsibilities for functional safety during the production, operation, service, and decommissioning phases.
Okay.
This includes defining access to and exchange of production monitoring records, especially for any safety-related special characteristics identified in the design. And results from failure analysis of returned parts that field data is crucial. They also establish timely communication channels for any safety-related events or required analyses that pop up later.
Wow, that's incredibly thorough. It really does sound like that complex construction project analogy holds up, where you have the architects, the structural engineers, the electricians, all these specialized firms. They absolutely have to meticulously coordinate their work through detailed contracts and regular reviews. Otherwise, the building isn't safe. The DIA really sounds like that central coordination mechanism designed to prevent catastrophic breakdowns in communication or responsibility.
That's an excellent analogy. It's precisely that coordination role. The key work products generated from this clause include the supplier selection report, how you chose them in the first place, the development interface agreement itself, the supplier's safety plan, the functional safety assessment report from the supplier, and the final supply agreement. These documents are the tangible evidence that these crucial interactions are being managed properly.
Okay, that leads us perfectly into the next foundational management process in Part 8, Clause 6. Specification and management of safety requirements. This sounds like the absolute bedrock of any safety-critical system. I mean, you can't clearly define what safe means for your system. How can you possibly build it?
It truly is the bedrock.
I get
You can't build what you can't define.
Okay.
The objectives here in Clause 6 are straightforward but incredibly important. First, to guarantee the precise specification of safety requirements, focusing particularly on their attributes and characteristics. And second, to ensure these safety requirements are managed consistently throughout the entire safety lifecycle.
Why are safety requirements given such central focus? Aren't they just, requirements like any other?
But they're far more than just requirements. They are the crucial directives, the instructions, for achieving and maintaining functional safety. They're typically structured hierarchically, becoming more detailed as development progresses through the different phases, from the high-level concept phase down to system, hardware, and software levels, as detailed in other parts of ISO 26262, like Parts 3, 4, 5, and 6.
Right, they get more specific further down the V model.
Exactly. And effective management isn't just about writing them down neatly. It involves obtaining agreement from all stakeholders, securing commitment from those who actually have to implement them, and maintaining crystal clear traceability for the top safety goals all the way down. The standard even explicitly recommends the use of suitable requirements management tools, which really hints at the sheer volume and complexity involved in managing potentially thousands of these requirements.
Oh yeah, doing this in a spreadsheet sounds like a nightmare. How exactly does ISO 26262 specify how these requirements should be written? Are there specific formats or notations preferred?
Yes, the standard Section 6.4.1 outlines the permitted methods. You can use natural language, just plain English sentences. But the standard advises that for more complex behaviors, semi-formal notations are often better.
Semi-formal? Like what?
Things like UML, Unified Modeling Language, or SysML, Systems Modeling Language, model-based techniques, or even structured templates with a controlled vocabulary. These help reduce ambiguity, For very precise, often low-level requirements where ambiguity could be catastrophic, formal notations based on mathematical logic are also an option, though less common due to the expertise required.
So the choice depends on the complexity.
Yes, and the knowledge of the people specifying and using them. The ultimate goal is always unambiguous clarity. Everyone needs to understand the requirement in the same way.
Okay, clarity and precision. What about the attributes and characteristics of these requirements themselves? What makes a good safety requirement in the eyes of ISO 26262?
This is where it gets really interesting and, frankly, quite challenging in practice. Section 6.4.2 details these crucial aspects. First, identifiability. Safety requirements must be unambiguously identifiable. Usually this means they're in a separate document or database or tagged with a special attribute like safety relevant.
Okay, easy to find.
Yes. Then, ASIL inheritance. Safety requirements inherit the automotive safety integrity level, the ASIL, from their parent requirements, unless you specifically apply ASIL decomposition, which is a technique detailed in Part 9 to split a high ASIL requirement into lower ASIL ones with additional independence arguments.
Right, the safety level flows down.
It does, an allocation. Each safety requirement must be clearly allocated to the specific item or element responsible for its implementation. You need to know who or what is supposed to fulfill this requirement.
That makes sense. But what about the core qualities of the requirement text itself? What should a perfect safety requirement look like when you read it?
This is the tough part. Section 6.4.2.4. The standard lays out a whole list of crucial characteristics. A good safety requirement should be unambiguous. Everyone involved must have a common, shared understanding of its meaning. No room for interpretation. Comprehensible. All stakeholders, including developers, testers, and managers, need to understand it clearly. Atomic or singular. Ideally, it shouldn't be possible to divide it into smaller, independent safety requirements at the same hierarchical level. Though the standard acknowledges this might sometimes conflict with other characteristics like comprehensibility, internally consistent, no contradictions within the requirement itself, feasible and achievable. It must actually be possible to implement it within the project's constraints, resources, technology, etc. Verifiable. This is key. There must be a defined way to check if the requirement has been fulfilled. Can you test it? Can you measure it? Necessary. It must define an essential capability or constraint. If you removed it, there would be a safety deficiency. No nice-to-haves. Implementation free. It should state what is required, not how it should be met. This avoids boxing designers into specific solutions too early. Complete. It should be clear without needing further explanation, ideally measurable, and fully describe the required capability. Conforming. It must adhere to any applicable government regulations, industry standards, or internal product standards.
Wow, that's quite a demanding checklist. It strikes me that while these characteristics seem almost self-evident, their absence is often the silent killer of safety projects, isn't it? A requirement that isn't truly unambiguous or verifiable creates this dangerous illusion of safety rather than providing real protection.
You're absolutely right. That illusion of safety is a major risk. It's easy to write something that looks like a requirement, but fails these tests.
Are there also specific attributes that must always accompany a safety requirement, like metadata?
Yes, Section 6.4.2.5 mandates certain attributes. Every safety requirement needs a unique identification, often a number or code that remains unchanged throughout the lifecycle. Think REQ SW21234. It also needs a clear status like proposed, accepted, implemented, verified, rejected, and of course, it's assigned ASIL.
Okay, unique ID, status, ASL. Got it. So you've specified them perfectly, following all those rules. How do you then manage this potentially huge set of requirements throughout the project, given they're likely to evolve and change?
Right, management is the next big challenge, Section 6.4.3. The standard requires the entire set of requirements to have certain properties as a whole. Things like a clear hierarchical structure, an organizational structure, maybe grouped by system architecture, completeness, meaning the set of requirements at one level fully implements the requirements from the level above, external consistency, no contradictions between different requirements, no duplication or very controlled redundancy, and overall maintainability.
And the most critical part of that management, I'm guessing, is traceability, linking everything together.
We got it. Traceability, 6.4.3.2, is explicitly highlighted as absolutely vital. Each safety requirement must be linked. Backwards to its source, the higher level requirement or safety goal it came from, forwards to its derived requirements at lower levels, or to its realization in the design, like specific code modules or hardware components. And crucially, forwards to its verification specification, the test cases or analysis methods that prove it's met, which is covered in Clause 9.
And why is this traceability so intensely emphasized?
Several reasons. It ensures consistency, that you're actually building what you intended. It's essential for impact analysis. If a high-level requirement changes, traceability tells you exactly which downstream designs, code, and tests are affected. Without it, change management is impossible. And it's fundamental for supporting confirmation measures like functional safety assessments and audits. Auditors will check these links to verify the safety case. This chain of links is absolutely non-negotiable for proving safety.
Makes sense. You need to be able to follow the thread. And what about verifying the requirements themselves? Not the implementation, but the requirements as written.
Good point. Section 6.4.3.3 covers verification of the requirements. Methods include things like peer reviews, walkthroughs, inspections, using semi-formal verification techniques, especially if you use models to specify them, and even formal verification methods for very high integrity requirements. And finally, tying it all together, all safety requirements must be placed under configuration management, which is the topic of Clause 7, to maintain their integrity and track changes over time.
Ah, perfect segue. Let's move on to Clause 7, configuration management. This sounds like, well, version control on steroids for absolutely everything safety related.
That's a pretty good description. It absolutely is. The objectives stated in the standard are clear. First, to ensure that all safety-related work products, items, and elements, and this includes not just the code or hardware designs, but also the requirements, test plans, tools used, even principles and conditions of their creation, can be uniquely identified and reproduced in a controlled manner at any time.
Reproduced, exactly.
Exactly. And second, crucially, to guarantee that the relationships and differences between earlier and current versions can be accurately traced. It's not just about managing files, it's about managing the entire evolving safety argument and all its constituent parts in a controlled way.
So if you need to roll back to a specific version of the system from 6 months ago, or understand exactly what changed between version 2.1 and 2.2 of, say, a safety concept document, you can do that with complete confidence.
Precisely. That's the core idea. Configuration management, CM, is of course a well-established practice in the automotive industry, often referencing standards like ISO 1007 or frameworks like Automotive SPICE. What ISO26262 does is make it explicit that every single work product generated or used in the entire ISO26262 lifecycle is subject to configuration management.
Every single one. That sounds like a lot.
It is. This isn't just for software code. It applies to hardware designs, requirement specifications, safety plans, test reports, analysis results, manufacturing instructions, user manuals, literally anything that contributes to the safety case or is needed to reproduce the item.
Wow. Okay. What are the key requirements for making this work effectively in practice?
The standard, Section 7.4, lays them out quite clearly. First, planning. Configuration management can't be an afterthought. It needs to be thoroughly planned up front. This plan typically includes defining responsibilities, allocating resources, selecting the right tools and repositories, defining identification schemes and naming conventions, setting up access rights, deciding on baselining schedules, and establishing release and approval procedures.
So a detailed plan is job number one.
Absolutely. Second, process compliance. The CM process itself must align with broader quality management system standards, like IETF 16949, and also any specific requirements for software development processes, like those in ISO 26262-Part. It needs to integrate smoothly.
So it connects to existing quality systems. It doesn't replace them.
Exactly. It builds on them and tailors them for safety. Third, baselining. Work products required by the safety plan and any others necessary to reproduce items and elements must be formally baselined, essentially, a snapshot taken at a significant point in time and placed under configuration management control according to the defined strategy. This freezes a known good configuration.
Right, creating stable milestones.
Precisely. Fourth, the strategy definition itself needs to clearly define the specific conditions or purposes throughout the entire safety lifecycle for which work products, items, and elements require unique identification and reproduction. For example, a baseline is always required before work products are exchanged in a customer-supplier relationship, as per the DIA.
Makes sense.
And finally, perhaps most importantly, continuous maintenance. Configuration management isn't something you do once. It must be actively maintained throughout the entire safety lifecycle, ensuring consistency and control from the initial concept phase all the way through development, production, operations, service, and even decommissioning.
This really is like the ultimate historical record for a product's safety aspects. I'm picturing the challenge, like you said before, of building multiple versions of a complex engine control unit over several years. Configuration management is the only thing that allows you to precisely recreate the software and hardware design of any given version shipped to a customer, identify exactly what components or code changed between versions, and understand why those changes were made. It ensures consistent and controlled updates and prevents utter chaos.
That's exactly the kind of scenario it's designed to handle robustly. Without it, managing complex safety systems over time would be impossible. The primary work product specifically called out for this clause is the Configuration Management Plan.
Okay. Moving logically from configuration management, we land on Clause 8, change management. Given how complex these E-systems are and how frequently things inevitably change during development, production, and even in operation with software updates, this has to be another absolutely critical piece of the puzzle.
It absolutely is. You can't freeze a design forever. The objective of Clause 8 is to systematically analyze and control all changes made to safety-related work products, items, and elements across the entire safety lifecycle. Change management provides that structured approach for planning, controlling, monitoring, implementing, and documenting any modifications.
Why is it so important?
Its primary importance lies in maintaining the integrity of the safety functions and properties despite these changes. And change is defined very broadly here. It includes fixing anomalies or bugs, removing features, adding new features or enhancements, dealing with the obsolescence of components, anything really. If it alters the original safety argument or the baseline configuration, it's a change that needs formal management.
So it's not just about fixing bugs, but literally anything that alters the original design or behavior as defined.
Exactly. And it's inextricably linked with configuration management, Clause 7, as you'd expect. You can't manage changes effectively if you don't have a clear, controlled record from your CM system of what the current configuration is that you're changing.
Yeah.
A well-defined interface and workflow between these two processes, CM and change management, is absolutely crucial for effectiveness.
Okay, that makes sense. What does the process actually look like when a potential change is proposed? This must be a highly disciplined process, right?
It has to be. Section 8.4 outlines the process requirements. It starts, like CM, with planning and initiation, 8.4.1. The change management process itself must be planned and initiated before any changes are actually made. This plan identifies which items are subject to change management, not necessarily everything, and defines the overall schedule and responsibilities.
Okay, plan first.
Then, every potential change kicks off with a formal change request, 8.4.2. Each request needs a unique identifier and must include key information like the date, the reason for the change, the why, an exact description of the proposed modification, the what, and the specific configuration baseline it applies to the from.
And after the request is logged, I'm guessing a thorough analysis of the potential impact is next.
Spot on. That's the change request analysis, 8.4.3, often called impact analysis, and it's arguably the most critical step in the whole process. For every single change request, an impact analysis must be performed. It looks at the involved item or element, its interfaces, and any potentially affected connected items.
What does that analysis need to cover?
It needs to address several things. The type of change, is it fixing an error, an enhancement, adapting to a new regulation? It needs to identify all affected work products, items, and elements across the system. If it's a distributed development, it identifies the responsible parties involved. But most crucially, the analysis must assess the potential impact of the change on functional safety.
That's the absolute key, isn't it? How does this proposed change affect the safety of the system? Could it introduce new hazards? Could it negate existing safety measures?
Absolutely. That's where safety professionals really earn their keep. And here's a core rule from 8.4.3.2 that underscores the rigor. Any change to a work product under configuration management shall initiate a return to the applicable phase of the safety lifecycle for subsequent activities needed to ensure compliance with ISO26262.
Whoa, hold on. So you don't just patch the code or tweak the design in isolation. You have to effectively go back to, say, the design phase or the testing phase for that change part.
That's essentially it. You re-enter the V-model loop at the appropriate point to ensure the change is properly designed, implemented, verified, and validated within the safety context. You don't just tack it on the side. This prevents changes from silently eroding the system's safety integrity.
Wow, that's a strict but necessary requirement. What happens after the impact analysis is done? Who makes the final call on whether to proceed?
Next comes change request evaluation, 8.4.4. Based on the findings of the impact analysis, authorized persons, this usually involves a change control board or key individuals like the project manager, safety manager, quality assurance lead, and relevant developers, evaluate the request and make a formal decision. Accept, reject, or maybe delay it. For accepted changes, they formally decide who will carry out the change and the target timeline, always considering any interface implications with other teams or suppliers.
Okay, a formal decision gate.
Yes. And finally, the process covers implementing and documenting the change, 8.4.5. Accepted changes must be implemented and then verified according to the plan. And here's another critical safety integration point, 8.4.5.2. If the impact analysis determined that the change does impact safety-related functions or properties, then the overall functional safety assessment for the item and any applicable confirmation reviews, like audits, must be updated to reflect the change before the changed item is released.
So the formal safety case documentation has to be updated and approved to reflect the new reality before anything goes out the door. You can't release first and update the paperwork later.
Precisely. The safety case must always reflect the current state of the released item. And the documentation of the change itself must be thorough, including a list of all changed work products with their new configurations versions, detailed specifics of the change implemented, and the planned deployment date or method. Importantly, even rejected changes and the rationales for rejecting them must be documented. This transparency and record-keeping are paramount for audits and future understanding.
This whole process brings to mind a very concrete scenario. Imagine a bug is discovered in the braking software of a vehicle that's already out in the field, in production. Change management dictates this precise process. A formal change request is raised. An exhaustive impact analysis is done. Could this bug cause unintended braking? Could it disable the ABS under certain conditions? What's the ASL implication? Then, a decision is made by a cross-functional team. The fix is carefully implemented and then rigorously retested, maybe even requiring regression testing of the whole braking system. And finally, if and only if the updated safety assessment confirms safety is maintained or restored, the software update can be deployed to vehicles, with all these steps meticulously documented. This is how you prevent a seemingly small bug from turning into a major recall, or worse.
That's a perfect real-world example of how absolutely critical this process is, especially for maintaining safety after a product has been initially released. The key work products specifically generated by this clause include the change management plan, the change request forms, the impact analysis reports and associated change request plans, and the final change report summarizing what was done.
Okay. So we've covered managing distributed developments, managing requirements, managing configurations, versions, and managing changes. That represents an enormous amount of information being generated and tracked. How does Part 8 ensure all of this is properly recorded, organized, and accessible when needed? This seems to take us naturally to Clause 10, documentation management.
Absolutely.
Yeah.
All those other processes generate outputs, and Clause 10 is about managing that output effectively. The objectives here are to establish a robust documentation management strategy that facilitates an effective and repeatable process across the entire safety lifecycle. Now, documentation management itself is, again, a standard practice in the automotive industry, often aligning with requirements from quality management systems like IATF 16949 or the more general ISO 9001. ISO 26262 doesn't reinvent the wheel here, but it focuses primarily on the content required for functional safety, rather than prescribing specific layouts or appearances for documents. The emphasis is squarely on what information needs to be captured and how it supports the overall safety case.
So it's about ensuring the right information is recorded, not necessarily about how pretty the document looks or what template you use.
Correct. Substance over style, although clarity is key. And importantly, documentation in the context of 26262 doesn't necessarily mean physical paper documents anymore. It can be, and often is, in various forms like electronic media databases, model files, wikis, often with automated generation tools involved. The standard also stresses the importance of avoiding unnecessary information duplication to aid maintainability. It's much better to use cross-references instead. Duplication can easily lead to inconsistencies when something changes, which is a big risk for safety.
Right. Change it in one place, forget the other 5 places it was copied. What are the key requirements for effective documentation management according to Clause 10?
Section 10.4 outlines them. First, like CM and change management, it requires a planned process. The documentation management process must be planned to ensure that the necessary documentation is available when needed for the effective completion of each safety lifecycle phase and all the verification activities, for the proper management of functional safety activities overall, and critically, as essential input to confirmation measures like audits and assessments. You need the documentation to prove compliance.
So if it's a work product mentioned anywhere in ISO 26262, it implicitly has to be documented. There are no exceptions for safety-related stuff.
That's the strong implication, 10.4.2. If the standard calls for a work product as an output of a required activity, then documentation containing the results of fulfilling those requirements is expected. The documentation itself needs certain qualities, 10.4.3. It should be precise, concise, clearly structured, easy for its intended users to understand, verifiable, meaning you can check its correctness, and maintainable over the long term.
Okay, basic good documentation practices.
Yes, but enforced for safety. The overall organizational structure of the documentation should align with the organization's in-house procedures, but must facilitate easy information retrieval. You might think of a well-organized digital documentation tree or repository structure, and each individual work product or document must include specific formal elements, 10.4.5. A clear title reflecting its scope, author, and approver information, accountability, unique identification for each revision or version, linking back to CM, a comprehensive change history, who changed what, when, and why, and a clear status indication, like draft, in review, released, obsolete.
So version control and history are built in.
Absolutely. And finally, it must always be possible to identify the currently applicable revision version of any document or piece of information consistent with the configuration management system, Clause 7. This link between documentation management and configuration management is vital for maintaining the integrity of the safety information landscape.
This all sounds like creating a safety net for information. If there's ever a question about why a certain design decision was made or what the result of a specific test was years down the line, you should be able to trace it all the way back through the documentation. I can easily imagine a scenario like a product recall for a safety-critical issue discovered years after launch. Effective documentation management means you can instantly pull up every relevant design specification, test report, change request log, and approval signature for that specific product version. That provides the data needed for root cause analysis, for planning corrective actions, and crucially, for demonstrating due diligence to regulators or in legal situations. It's fundamentally about accountability and enabling continuous improvement based on past experience.
That's a perfect illustration of why it's so critical, especially in the long term. The work products specifically mentioned for this clause are the documentation management plan and potentially documentation guideline requirements for the organization. Okay, so that covers the core management supporting processes. Shall we transition now to the equally critical struggle? Key technical supporting processes also outlined in Part 8. These get more into the nuts and bolts.
Yes, let's do that. Let's start with Clause 11, confidence in the use of software tools, which is often referred to as software tool qualification. I imagine that with so much of modern vehicle development being software-driven, the tools you use to create and test that software need to be trustworthy themselves, right? I mean, a subtle bug in a compiler could potentially create a very dangerous hidden problem in the final code.
You've hit the nail right on the head. That's the exact concern driving this clause. The objectives stated are, first, to provide clear criteria for determining the necessary level of confidence you need in any software tool used in safety-critical development. And second, to establish methods for actually qualifying these tools, which means providing objective evidence that they are suitable and can be relied upon for the specific tasks required by ISO26262-Part.
So we're not just talking about the safety-critical code itself, but the tools used to create it, like the compilers, the modeling tools, the code generators, the test execution environments, the static analysis tools, basically anything that touches or analyzes the safety-related item during its development.
Exactly. It covers a wide range of software tools, whether they're commercial off-the-shelf, COTS tools, open source tools, or even tools developed in-house. They're all integral to modern development workflows. The core concern, as you said, is minimizing the risk of systematic faults being introduced into the developed product because of a malfunctioning tool, or the risk of a tool failing to detect faults that are already there. It's also about ensuring the overall development process remains adequate, even when you're relying heavily on these automated tools.
Okay. So the level of rigor you apply to a tool depends on its potential impact.
Precisely. The rigor of the requirements for qualifying a tool depends on its specific role in the development process, the potential risks associated with its failures, what could go wrong if the tool messes up, and the maximum ACL of the item or element it's being used to help develop. You wouldn't apply the same rigor to a simple text editor as you would to a code generator for HLD software.
That makes sense. How do you actually determine how much confidence you need in a particular tool? Is there some kind of scale or classification?
Yes. The standard defines a process for determining the tool confidence level, or TCL. It's a value from TCL 1, lowest confidence needed, to TCL 3, highest confidence needed. Calculating the TCL involves assessing two key factors, as defined in Section 11.4.5, tool impact, TI, and tool error detection, TD.
Okay, tool impact, TI. What does that measure?
Tool impact assesses the possibility that a malfunctioning tool could introduce errors into the safety-related item or fail to detect existing errors in it. It has two levels. TI1 means there's realistically no such possibility. For example, this might apply if the tool's output is completely and rigorously verified by other independent means, like a 100% manual review or verification using a diverse, independently validated tool. TI2 covers basically all other cases where there is a possibility, however small, that the tool could introduce or fail to detect relevant errors. This is the more common case.
Okay, TI1 is no impact possible. TI2 is impact possible. What about tool error detection, TD?
TD assesses your confidence in the measures within your development process that are capable of preventing the tool from being used incorrectly or detecting malfunctions or errors produced by the tool. It has three levels. TD1, high confidence in prevention or detection measures. An example might be if code generated by a tool is subsequently 100% verified through formal methods or exhaustive testing covering all possible behaviors. TD2, medium confidence. For instance, if a tool performs static analysis to find bugs, but you also apply significant dynamic testing to the software it analyzed, one measure backs up the other, but neither is perfect. TD3. Low confidence, meaning there are no systematic measures in place to detect errors introduced or missed by the tool. Malfunctions would likely only be detected randomly later on, perhaps during integration testing, or even in the field.
Right, so TD1 is high confidence in catching errors, TD3 is low confidence, and then these two factors, TI and TD, are combined to determine the overall tool confidence level, the TCL. How does that work?
Yes, they're combined using a simple matrix, Table 3 and Part 8. If the tool impact is TI1, no impact possible, the resulting TCL is always TCL1, the lowest level. Makes sense, right? If it can't hurt anything, you don't need high confidence. If the tool impact is TI2, impact possible, then. If the tool impact is TI2, impact possible, then. Combined with TD1, high detection, you get TCL1. Strong detection measures compensate for the potential impact. If the tool impact is TI2, impact possible, then. Combined with TD2, medium detection, you get TCL2. If the tool impact is TI2, impact possible, then. Combined with TD3, low detection, you get TCL3, the highest confidence level needed. This is the riskiest scenario the tool could cause problems, and you have little confidence you'd catch them.
Okay, TIT-TD3 is the highest risk, needing TCL3. What if it's unclear what the TI or TD should be?
The standard is clear. If TI or TD is uncertain, you must make a conservative estimate. Generally, this means assuming higher impact, TI2, and lower detection, TD3, leading to a higher TCL. You err on the side of caution.
Makes sense for safety. So once you've determined the required TCL for a tool, say it's TCL2 or TCL3, how do you actually qualify the tool to meet that level? What does the qualification process involve?
Okay, Section 11.4.6 covers the qualification methods. For TCL1, the standard says no specific qualification methods are required beyond selecting the tool appropriately. For TCL2 and TCL3, however, you need to apply a combination of methods to gain the necessary confidence. The standard provides tables, highly recommended plus, recommended plus, or no recommendation no, depending on the ASL of the project. These methods fall into a few categories.
What are the main methods?
There are three main ones described. 1. Increased confidence from use, 11.4.7. This is basically arguing that the tool is reliable because it has a proven track record. You need evidence of previous usage in comparable contexts. Sufficient and adequate historical data, proof that the tool's specification hasn't changed, and records showing systematic collection of malfunction data during that past use. 2. Evaluation of the tool development process, 11.4.8. Here you gain confidence by showing that the tool itself was developed according to an appropriate standard, like IEC 61508, maybe even ISO26262 itself, or RTCA DO 178C for avionics, or at least a suitable, rigorous software development process, like one assessed highly using automotive SPICE. You're trusting the tool because it was built well. 3. Validation of the software tool, 11.4.9. This involves actively testing the tool. You need evidence that the tool complies with its own specified requirements. This often involves creating specific test suites, analyzing any malfunctions found during this validation testing, and examining how the tool reacts to anomalous operating conditions or inputs.
So you can use a mix of these. Past experience, how it was built, and direct testing.
Exactly. For TCL2, and especially TCL3, you typically need to combine evidence from multiple methods to build a convincing qualification argument. The qualification activities and results must then be documented in a software tool qualification report.
This reminds me of the compiler example again. If you're using a compiler for, say, ASIL-D breaking software, and you determine it needs TCL3 because a compiler bug could introduce a fault that's hard to detect later, TI2-TD3 scenario, then you'd need rigorous qualification. You might need to show evidence of its widespread successful use, confidence from use, maybe get information from the vendor about its development process, evaluation of development, and definitely perform extensive validation testing using code structures typical of safety-critical systems validation. It's a significant undertaking, highlighting a hidden risk if it's not managed.
That's a perfect example of applying the process. It ensures the tools enabling safety aren't inadvertently undermining it. The key work products coming out of this clause are the Software Tool Criteria Evaluation Report, documenting the TITD TCL analysis, and the Software Tool Qualification Report, documenting the evidence. Okay, next up we have Clause 12, Qualification of Software Components. This sounds related to tools, but it's distinct, right?
Yeah, what's the key difference here? We talked about tools assisting development. What are software components in this context?
Good question. The distinction is crucial. A software tool, as we just discussed, is something that assists in the development or verification process, like a compiler, a static analyzer, a modeling tool, but it doesn't typically end up in the final embedded product shipped in the vehicle. A software component covered in Clause 12 is a piece of code or a software unit that does become part of the final safety-critical item running in the vehicle. Think of things you might buy off the shelf or reuse from a previous project.
Okay. So this is about reusing code, maybe commercial off-the-shelf COTS software, or libraries, or maybe even code from another non-automotive division of the company.
Exactly. The objective of Clause 12 is to provide concrete evidence that these pre-existing or third-party software components are suitable and safe enough for reuse within a safety-critical item being developed under ISO 26262. The motivation is clear. Avoid reinventing the wheel, reduce development time and cost by leveraging existing functionalities.
Makes sense. So what does software component cover?
The standard defines it quite broadly. It could be source code, models that generate code, precompiled object code, or fully compiled and linked software. Examples include third-party libraries like a math library or a communication stack, drivers, real-time operating systems, RTOS, or even components developed in-house previously but perhaps not originally developed according to ISO 26262.
Okay, pretty broad. What are the requirements for qualifying these components? This sounds like it could be a deep rabbit hole, especially if you didn't develop the component yourself.
It can be quite involved, yes. Section 12.4 lays out the requirements. First, you need a comprehensive component specification. 12.4.2.1. Even if you didn't write it, you need to document what it is and does. This specification must include unique identification, name, version, the maximum target ASIL that could potentially be violated by its incorrect performance. Details the activities performed for its qualification. The component's own requirements, functional requirements, any known safety requirements, details on algorithm accuracy or numerical precision, its behavior in case of internal failures, performance like response time, resource usage like memory CPU, the required runtime environment, its robustness under stress or overload conditions. Requirements specifically for its intended use in your system. A description of its configuration, including any subunits if applicable. Its required and provided interfaces, including any shared resources it uses. An application manual and clear instructions for correct integration, including any necessary development tool parameters or settings. Its documented reactions to anomalous operating conditions, like handling interrupts or re-entrant calls. And importantly, a description of any known anomalies or bugs, along with defined workarounds if they exist.
Wow, that's incredibly detailed. So even if you buy a component, you need to gather or create documentation that covers all of that. You need to know almost everything about its internal behavior and limitations.
Absolutely. You're taking responsibility for its safety within your system, so you need that deep understanding. Beyond just the specification, you need evidence of compliance. 12.4.2.2. This means verification must demonstrate that the component meets its specified requirements. This is primarily done via requirements-based testing, and you could potentially reuse previous test results if they are suitable and properly documented.
What does the testing need to cover?
It must cover both normal operating conditions and the specified failure behavior. And critically, it must provide evidence that there are no known errors in the component that could lead to a violation of any safety requirements allocated to it in your system. For components intended for ASIL-D applications, the standard adds a requirement, called 0.4.2.3, that structural code coverage must be measured during testing, as per ISO 2626262 Clause 9, to provide confidence in the completeness of the test cases.
Structural coverage for ASIL-D reuse. Okay.
And a very important point. This verification and the resulting qualification are only valid for an unchanged implementation of the software component. If the supplier gives you a new version, even with just minor bug fixes, you technically need to reevaluate its qualification status.
Right, because the change could have unintended consequences.
Precisely. And all of this qualification effort, the specification, the verification results, the analysis must be thoroughly documented in a qualification report 12.4.2.5. Finally, the results and the overall validity of the software component's qualification for its intended use must themselves be verified, 12.4.3, typically through reviews, as part of the standard verification process, Clause 9.
This sounds like a significant amount of work just to use something off the shelf, especially compared to just grabbing a library and non-safety critical development. But I guess the alternative is building it all from scratch to full ISO 26262 compliance, which might be even more work or impossible for some complex components like an RTOS.
It often is a lot of work, but it's deemed essential for ensuring safety when reusing software black boxes. It forces a rigorous assessment. Think about needing a sophisticated real-time operating system, RTOS, for a new vehicle control unit. Developing one from scratch to meet ISO 26262 requirements is a massive undertaking, so the team might want to use a commercially available RTOS. Software component qualification, Clause 12, is the defined process for rigorously assessing that COTS RTOS. You need to ensure its pre-existing design, its documented behavior, and its existing testing are robust enough for your specific safety-critical context, covering its failure modes, resource usage, timing behavior, and how it interacts with other safety functions. It avoids reinventing the wheel, but only if that pre-existing wheel is demonstrably safe for your specific vehicle application and ASL.
Okay, that clarifies the software side. That logically brings us to Clause 13, evaluation of hardware elements. This feels like the parallel process for the physical stuff, the chips and sensors.
You're right, it's very much the hardware equivalent, but with some key differences due to the nature of hardware. The objective here is twofold. First, to ensure that a hardware element's functional behavior is sufficient to meet the safety requirements allocated to it, thereby minimizing the risk of a safety goal violation due to systematic faults, design flaws, in the hardware. Second, it's important to note up front that this clause primarily addresses systematic failures. The suitability of the hardware element regarding random hardware failures, like things just wearing out or failing unpredictably, is typically evaluated and managed at the next higher level of design integration, using techniques like hardware architectural metrics, SPFM, LFM, and safety analyses like FMIDA, defined in ISO 26262-5.
Okay, so Clause 13 is mainly about avoiding design flaws in reused hardware.
Primarily, yes. It provides an alternative means of compliance with the hardware development requirements in ISO 26262-5. It's intended for situations where you're using COTS hardware components, like standard microcontrollers, sensors, or power components, or perhaps custom hardware parts that were not originally developed according to ISO 26262, but are now being considered for use in a safety-related function.
So, similar motivation to software component qualification reuse. How do you evaluate these hardware elements? Are there different categories based on how complex they are?
Yes, absolutely. Hardware evaluation isn't one size fits all. Section 13.4.1.1 classifies hardware elements into 3 distinct classes based on their complexity and the visibility you have into their internal workings. Class 1. These are the simplest elements. Think basic passive components or simple semiconductors like resistors, capacitors, diodes, individual transistors. They have at most a few well-defined states, are considered fully characterizable, testable, and analyzable from a safety perspective. Their potential failure modes, like open, short, drift, can usually be identified without needing detailed implementation knowledge. Crucially, they don't contain any internal safety mechanisms relevant to the system safety concept. Class 2. These are more complex than Class 1, but still considered analyzable without needing full, detailed implementation information. They might have a few operating modes or limited value ranges. Good documentation from the supplier usually allows for adequate analysis. Examples could include things like standard Hall effect sensors, basic fuel pressure sensors, or standalone analog-to-digital converters, ADCs, that don't have complex internal logic or safety mechanisms relevant to your safety concept. Class 3. These are the highly complex elements. Think microprocessors, complex microcontrollers, MCUs, system-on-chips, SOCs, or digital signal processors, DSPs. They often have numerous operating modes, wide value ranges, complex internal architectures, and many parameters that require detailed implementation knowledge to fully understand. Sources of potential systematic faults, design bugs, are often only understandable with knowledge of the detailed implementation, the development process used, or even the production processes. And the key differentiator. Class 3 elements often do have internal safety mechanisms like memory protection units, watchdogs, calculation checks that are relevant for achieving the overall safety concept.
Okay. Class I simple, Class 2 moderate, Class 3 complex with internal safety features. So does the evaluation process differ significantly based on the class?
It does, quite significantly. For Class I elements, 13.4.2, due to their inherent simplicity and well-understood failure modes, the standard says they don't need to be evaluated by themselves under this clause. Instead, the focus shifts to the next level up. The hardware part or component into which these Class I elements are integrated must be developed in full compliance with ISO26262-Part. Their safety is managed at that integration level. For Class 1 elements 13.4.2, due to their inherent simplicity and well-understood failure modes, the standard says they don't need to be evaluated by themselves under this clause. Instead, the focus shifts to the next level up. For Class 2 elements 13.4.3, a formal evaluation is required. This typically uses an appropriate combination of analysis like stress analysis, interface analysis, and testing. You need to develop a detailed evaluation plan outlining the strategy. A comprehensive evaluation argument must be documented, demonstrating that its functional performance is compliant and adequate for the intended use, often based on supplier data sheets, analytical methods, potentially existing test results, or operational experience data. If testing is part of the evaluation, a specific test plan is needed, covering functions, allocated safety requirements, test sequences, conditions, pass-fail criteria, and potentially robustness testing as per ISO 26262-5. The results are compiled in an evaluation report.
Right, so Class 2 needs a plan evaluation with analysis and/or testing. What about the really complex ones, Class 3? The MCUs and SOCs?
This is where it gets most challenging. The standard explicitly notes in 13.4.4 that developing Class 3 elements in full compliance with ISO 26262 is generally the preferred approach. Why? Because proving the absence of systematic faults in such complex devices without having followed a rigorous safety development process like 26262 from the start is extremely difficult.
But sometimes you have to use a COTS microcontroller, right?
Exactly. So if evaluation is used as an alternative for Class 3 elements, they must, at a minimum, meet all the requirements specified for Class 2 elements: the plan, the argument, the analyzing, the report. But critically, additional measures are required on top of that to build a convincing argument that the risk of systematic faults is sufficiently low for the target ASIL link.
Additional measures, like what?
The standard suggests several possibilities. These could include demonstrating high verifiability of the specific safety-related functionality you're using within the complex chip, leveraging extensive relevant field experience data, though similar to proven in use, which we'll discuss next. This is often considered only a partial supporting argument for systematic faults in a hardware evaluation. Implement and supervision of the Class 3 element by an independent, diverse element in your design, coupled with a thorough dependent failure analysis, DFA detailed in ISO 26262-9, to ensure they don't fail together. Providing evidence that the Class 3 element was actually developed in compliance with a different but comparable safety standard, like maybe one from avionics or industrial control, that achieves a comparable integrity level.
That makes sense. You need extra layers of evidence of protection for these complex COTS parts if they weren't originally built to 26262. So, for example, if you wanted to use a complex microprocessor from a general electronics supplier, one not specifically designed for automotive safety under ISO 26262 and say a critical engine management system, maybe ASIL C or D, you'd first classify it as Class 3. This triggers the need for a deep dive into its known behaviors from data sheets, its potential failure modes, maybe using supplier FMATAs if available, and then demonstrating its safety through rigorous analysis and testing focused on your specific use case. And on top of that, you'd likely need to combine this with other arguments like significant relevant field experience for that specific chip, or perhaps implementing redundant safety mechanisms in your surrounding design to mitigate the inherent risks associated with using a non-26262 complex hardware element. It's a pragmatic approach, but it demands a strong safety justification.
Precisely. It acknowledges the reality of CRTES hardware use while demanding a robust safety argument. The key work products generated here are the hardware element evaluation plan, the hardware element test plan, if testing is performed, and the final hardware element evaluation report. This whole topic of reusing elements leads us very naturally to the next technical supporting process. Clause 14, the proven in use argument.
Ah, proven in use. This sounds like leveraging components or systems that already have a successful track record out there in the real world, right? Seems like common sense, but how do you formally prove something is proven in use for safety?
Exactly. It sounds intuitive, but the standard sets a very high bar. The objective of Clause 14 is to provide another alternate means of compliance with certain ISO 26262 requirements, specifically for reusing existing items or elements, which could be hardware, software, or even entire systems or functions, where extensive, high-quality field data is available to demonstrate their safety performance in real-world operation.
So it applies to things that are identical, or very nearly identical, to products already released and running in vehicles.
Yes, identical or with very high commonality. It's important to clarify, though, that proven in use is not simply about interchangeability or functional equivalence. The candidate product must meet specific, very rigorous criteria defined in this clause to get this credit.
What's the typical motivation for using this argument? When would a team turn to Clause 14?
Several common scenarios. Maybe carrying over an existing successful automotive application, or ECU, to a new vehicle platform with minimal changes. Perhaps adding minor new functions to an existing ECU that has a long history. Using components or systems that were designed and released before ISO 26262 was widely adopted but have shown excellent field history. Or incorporating widely used COTSS products, maybe even from other industries, where massive amounts of operational data exist.
Okay. What kind of evidence do you need to build this argument?
The argument needs to be substantiated by solid evidence, including detailed documentation on the candidate item itself, records from configuration management showing it hasn't changed significantly, records from change management documenting any changes that have occurred, and crucially, high-quality field data related to any observed safety incidents or failures during its operational life. Key considerations are the statistical relevance and quality of the field data, and a thorough analysis of any changes made to the candidate since the period the field data covers.
Does proven in use cover all types of failures?
It addresses both systematic failures, by arguing that if significant design flaws existed, they would likely have shown up in the extensive field operation, and random hardware failures, by providing statistical evidence of failure rates. However, the standard explicitly notes that a standard proven in use argument typically does not address failures related to aging or wear-out mechanisms unless specific analysis for that is included.
Right, because past performance doesn't guarantee future performance if things wear out.
Exactly. And another important point, even if you successfully use a proven-in-use argument for an element, the project-dependent safety management activities like including it in the safety plan, performing integration testing, and conducting confirmation measures like assessments for the overall item are still required. You can't just drop a proven-in-use component in and assume the whole system is safe without proper integration and verification.
Okay. How does a team actually get formal proven-in-use credit? What's the bar for deciding something is truly proven enough for a given ASIL?
Section 14.4.2 explains that the credit can only be claimed if the candidate component or item complies with all the detailed requirements of Clause 14. Using this argument must be planned up front, as per ISO 26262, and the credit granted is limited only to the specific safety lifecycle subphases and activities that the proven-in-use argument demonstrable covers. For example, we might cover design and verification, but not necessarily production conformity. Integration measures and the final safety validation of the overall item that embeds the proven-in-use element are still absolutely required. And the confirmation measures, audits, assessments for the overall item must explicitly consider and evaluate the proven-in-use arguments and the supporting data.
And you mentioned changes are critical. What if the proven component has been modified?
That's a huge point, 14.4.4. Any modification to an item or element claimed as proven in use must undergo specific analysis for the credit to be maintained. Even seemingly minor changes could invalidate the argument based on past field data.
So a small bug fix or a component swap could potentially require you to abandon the proven-in-use claim and revert to standard development compliance.
Potentially, yes, or at least require a very strong argument that the change does not affect the validity of the historical data. You need minimum information on the candidate, 14.4.3, including its identification, requirements, and previous use context. And the analysis of modifications is key. You must identify all design and implementation changes, as well as any changes to the intended operating environment compared to its previous use. Modifications introduced specifically for the new application must comply with the standard ISO 26262 change management process, Clause 8, and if modifications were made independent of the new application, like ongoing bug fixes by the original supplier, evidence must be provided that the proven-in-use status remains valid despite those changes.
Okay, managing changes is vital. What about the field data itself? How is that analyzed? You mentioned potentially mind-boggling numbers earlier.
Yes, the analysis of field data, 14.4.5, is where it gets statistically intense. First, you need evidence from configuration and change management that the candidate was under robust control during and after the period used for evaluation. Then, you need to establish target values for proven in use, 14.4.5.2. This involves calculating the total evaluation period, total observation time aggregated from all specimens in the field. The observation period for each individual specimen must exceed a reasonable threshold, like the average yearly vehicle operating time.
And the numbers.
For a full proven-in-use status for a given safety goal, the evaluation period must statistically demonstrate compliance with that safety goal based on observable incident rates related to the candidate, calculated typically with a 70% lower confidence level, using methods like the chi-square distribution. The target incident rates are extremely low, mirroring the targets for residual risk in ISO26262. For example, for an ASIL-D-related safety goal, the target observable incident rate linked to the candidate would need to be less than 10 to 9 failures per hour.
Less than 1 failure in a billion hours.
That's the kind of reliability level needed for the highest ASIL using this argument. To demonstrate this with 70% confidence using the chi-square method, you'd need a cumulative evaluation period of approximately 1.2 by 109 hours, 1.2 billion hours, without observing any relevant safety-critical incidents caused by the candidate.
Billions of hours without incident. That's absolutely staggering. So we're talking about components or systems that have been running essentially flawlessly from a safety perspective in potentially millions of vehicles for many, many years.
Exactly. It sets a very high statistical bar, especially for higher ASILs. The standard does allow for an interim period with slightly higher allowable incident rates for provisional application while more data is gathered. But if any relevant incident is observed during this period, you either have to revert to the stricter rates or provide robust proof that the root cause has been eliminated and won't recur. As mentioned, additional measures are also needed if the candidate is susceptible to non-constant failure rates due to factors like wear or aging.
And you need a system to track problems?
Yes. A documented problem reporting system must have been in place to record and allow retrieval of any observed safety-impacting incidents caused by the candidate during its operational period. You need evidence that you would have known if something went wrong. Transparency is paramount.
This makes me think of a component like an anti-lock braking system, ABS module. If a specific ABS module model has been successfully used in, say, tens of millions of vehicles over a decade, accumulating maybe 10 billion operational hours with extremely few documented safety-related incidents attributed to it, then the proven in use argument under Clause 14 allows the manufacturer to leverage this extensive field data as a primary demonstration of that module's functional safety for a new vehicle program using the same module. It avoids having to redo all the original ISO 26262 development and verification steps from scratch. It's a potentially huge efficiency gain, but only justifiable if the component meets those incredibly high statistical bars and the usage conditions remain comparable.
That's the essence of it, perfectly captured. It's powerful but demanding. The key work products are the description of the candidate item for the proven in use argument and the detailed proven in use analysis reports containing the data and statistical justification. Okay, now the next two clauses, 15 and 16, are interesting because they are specifically designated as applicable primarily to trucks and buses, TMB, in the 2018 edition of the standard. They reflect some unique aspects of the heavy vehicle industry.
Right, TMB specific. Let's start with Clause 15, interfacing an application that is out of scope of ISO 26262. What makes this situation unique or more common for trucks and buses?
Well, the TMB industry often involves a multi-stage manufacturing process. You might have a company manufacturing the base vehicle chassis, which likely follows ISO 26262, and then a completely separate company, often called a bodybuilder or upfitter, extensively modifying that chassis or adding specialized equipment, like a crane, a refuse collection system, a concrete mixer. This creates unique safety interfaces between the 26262 compliant base vehicle and the potentially non-26262 equipment added later, interfaces not typically seen to the same extent in standard passenger car manufacturing.
Okay. So this clause addresses that specific business model.
Exactly. Its objective, specifically for TMB, is to gain confidence that an application or equipment added later, which was not developed to ISO 26262 standards. Maybe it follows a different standard like the Machinery Directive for industrial equipment, or maybe no formal safety standard at all, will not compromise the safety goals of the original ISO 26262 compliant base vehicle or item it's being integrated with. The focus is entirely on managing that interface between the compliant part and the potentially out-of-scope application.
So it's all about controlling the interaction point to prevent the non-26262 part from causing safety issues in the 26262 part. How do they manage that interface safely?
The standard, section 15.4, outlines the key requirements. The responsibility falls heavily on the base vehicle manufacturer or the supplier of the specific ISO26262 item being interfaced with to communicate crucial information and clear instructions to the integrator, the bodybuilder. This communication must include which systems and components of the base vehicle are permitted to be modified or interfaced with. What are the permitted system safety limits and specific safety requirements for any modifications or connections made? Are there specific safety measures that the integrator is required to apply during the integration?
So the base manufacturer provides a rulebook for the integrator.
Essentially, yes, a guideline or interface specification. The standard assumes the integrator, the bodybuilder, has the necessary capability to understand and follow these instructions. NG. Perhaps they comply with other relevant safety standards for their equipment, have an appropriate safety culture, and a functioning quality management system. If the integrators need to deviate from the provided assumptions or limits, for example, maybe they need to activate a power takeoff, PTO, during driving, which the base vehicle wasn't designed for, they're required to contact the base vehicle manufacturer to agree on specific safety requirements or solutions, potentially involving defining an ASIL equivalent level derived from the other standard being used. It boils down to clear communication, defined boundaries, and collaboration when deviations are needed.
So the burden is primarily on the base vehicle manufacturer to provide very clear guidance and restrictions, and then on the integrator to understand and adhere to them strictly. Like your example, a chassis manufacturer supplies a truck chassis, compliant with 26262, to a company that builds specialized refuse collection vehicles, which might comply with a different industrial machinery safety standard. Clause 15 guides how the chassis manufacturer communicates to the bodybuilder exactly how the chassis' EE systems, like CAN bus signals, power supplies, can be safely interfaced with the refuse collection equipment's controls, ensuring that these additions don't unintentionally interfere with or violate the truck's fundamental safety functions like braking or steering.
Precisely that scenario. The key work product mentioned here is a base vehicle manufacturer or supplier guideline documenting these interface requirements. Now, closely related, but distinct, is Clause 16, integration of safety-related systems not developed, according to ISO 26262, also marked as T&B specific.
Okay, what's the distinction here? This sounds very similar to the last one, integrating something not developed to 26262.
Good question. The nuance is important. Clause 15, which we just discussed, was about interfacing with an application that might be entirely out of scope of functional safety standards altogether, or follows a standard from a completely different domain, like industrial machinery. Clause 16, however, deals with integrating a safety-related system or component that is considered safety-related and was developed according to a different recognized functional safety standard, just not ISO 26262. Examples given include standards like IEC 61508, the parent standard, ISO 13849 for machinery safety control systems, ISO 25119 for tractors and agricultural machinery, or potentially even robust company-specific internal safety processes.
Okay. So Clause 16 is about integrating a component that did follow a formal safety standard, just not the automotive one, ISO 26262. Still primarily a P&B scenario?
Yes. The standard marks it as T&B specific, likely due to the supply chain complexities and use of components from related heavy equipment industries in trucks and buses. The objective here is to ensure that such a system or component meets the necessary functional safety level required for its integration into the overall ISO 26262 compliant item. The standard does include a note suggesting that developing the component according to ISO 26262 is generally favored, partly because demonstrating equivalence between different safety standards in the integration scenario described here can sometimes lead to higher effort and costs due to the need to bridge potentially different safety philosophies, methods, and requirements.
Right. Translating between standards can be tricky. So how is this bridging done? How do you prove compatibility between, say, an ISO 13849 component and an ISO 26262 system?
Section 16.4 specifies the key requirements. First, the integrator, the company following ISO 26262, must provide a clear safety rationale in their overall safety case. This rationale needs to justify why they are applying this clause, for example. The critical sensor needed was only available from a supplier who developed it according to IEC 61508 for these technical reasons.
Okay, justify the approach.
Yes. Then, the integrator must define the specific criteria they will use to demonstrate that the safety-related system developed to the other standard achieves the required level of functional safety for the intended function within the 26262 system. This is the core technical challenge. It might involve mapping integrity levels, for example, mapping an ASIL B requirement to an equivalent performance level D from ISO 13849 or SL2 from IEC 61508, and performing a rigorous comparison of the requirements from both standards regarding things like applied development methods, required failure rates for random hardware failures, diagnostic coverage expectations, and handling of systematic failures.
Oh, a detailed cross-standard comparison based on the specific needs.
Exactly. And finally, the integrator and the supplier of the non-26262 component must agree on a relevant set of measures to verify that these defined criteria are actually met. This verification provides the objective evidence.
What kind of verification measures are we talking about here? What might they agree on?
The standard gives examples. This set of measures could include things like ensuring the availability and adequacy of the system specification from the other standard, reviewing evidence of compliance via existing test reports generated according to the other standard, performing structured design analysis focused on systematic faults, perhaps using FEBA or FTA, if not adequately covered by the other standards process, gathering evidence of suitability for the intended automotive environment and operating conditions, looking for evidence of a robust product release process based on an adequate approval procedure, like PPAP production part approval process, common in automotive, potentially requiring additional design verification or validation testing specifically for the automotive context. For example, more stringent environmental testing, robustness testing, or highly accelerated life testing (HALT). Analyzing available field data for the component similar to proven in use. It's about building a convincing evidence-based argument that the component developed under the other standard provides an equivalent level of safety assurance for the specific requirements allocated to it in the ISO 26262 system.
So this is essentially about building a safety bridge between two different, potentially complex regulatory or standardization frameworks to ensure overall safety compatibility for the integrated system. So if an automotive Tier 1 supplier who follows ISO 26262 wants to integrate a sophisticated sensor system needed for a new truck braking function and finds the best sensor available was originally developed for a heavy industrial application following IEC 61508, then Clause 16 provides the framework. The Tier 1 integrator evaluates the IEC 61508 compliance sensor against the ASIL requirements of the braking function, defines their own specific acceptance criteria, mapping SIL to ASIL, comparing methods, and then agrees with the sensor supplier on potentially additional verification steps needed to ensure that sensor's safety level is truly compatible with the high demands of the ISO 26262 compliant truck braking system.
That's a perfect application scenario for Clause 16. It allows integration, but demands a rigorous justification. The key work products specifically mentioned is the documented safety rationale. Okay, that covers the main technical supporting processes. Now, while they aren't standalone clauses within Part 8 itself, they are actually detailed in Part 2 of the standard, we absolutely have to mention functional safety audits and functional safety assessments. Why? Because these crucial confirmation measures, as the standard calls them, are fundamentally enabled and informed by the diligent execution of all the supporting processes in Part 8 that we've just spent time discussing.
Ah, right. So audits and assessments are the checks that verify if all these supporting processes, requirements, CM, change management, documentation, qualification, etc., were actually done correctly. They're like the final exam for the safety process itself.
That's a great way to think of it. They provide an independent, objective evaluation to confirm that the functional safety activities performed and the resulting work products generated, which rely heavily on Part 8 processes, actually comply with the requirements of the ISO 26262 standard.
What's the difference between an audit and an assessment?
Good question. They have distinct focuses. A functional safety audit primarily aims to verify the implementation of the defined functional safety processes and plans. Are the teams actually following the procedures laid out in their safety plan, their CM plan, their change management process?
So auditing the how. Do they follow the rules?
Exactly. We saw an integration example when we discussed distributed developments back in Clause 5. The Development Interface Agreement, DIA, must explicitly include an agreement allowing a customer-assigned auditor to perform functional safety audits at the supplier's premises. This gives the customer confidence that the supplier's safety processes are indeed being followed in practice, not just existing on paper.
Okay, that's the audit. What about the functional safety assessment then?
A functional safety assessment has a broader purpose. It aims to confirm that the functional safety activities performed and their results, the actual work products, the safety case arguments, comply with ISO 26262 requirements. It's essentially a rigorous objective review of the evidence of safety that has been built throughout the life cycle. Is the safety case convincing? Does the evidence support the safety claims?
So, assessing the what. Did they achieve safety?
Precisely. And again, we saw links back to the DIA. For supplier-developed elements with higher ASILs, B, C, or D, the DIA specifies which organization performs these assessment activities. It could be the supplier themselves, the customer, or an independent third party. The supplier is then required to provide functional safety assessment reports to the customer, evaluating whether the developed elements actually meet the safety requirements they received and whether the implemented processes and generated evidence satisfy the functional safety criteria for the required ASIL.
And you mentioned earlier there's a critical link between assessments and change management too, right? That if something safety-related changes, the assessment has to be revisited.
Indeed, that's a crucial integration point we discussed under Clause 8, specifically 8.4.5.2. If any change to a work product managed via the change management process is determined through impact analysis to affect safety-related functions or properties, then the overall functional safety assessment for the item and any applicable confirmation reviews must be updated to reflect that change before the changed item is released.
That's a huge implication. It ensures the assessment remains valid and reflects the current state of the product. So the overall significance of these confirmation measures, audits, and assessments is really as independent gatekeepers, providing that ultimate objective proof that the system is safe.
Absolutely. They leverage all the detailed work products, the traceability, and the controlled processes ensured by the supporting processes in Part 8, like documentation management, configuration management, requirements management, change management, to provide that essential objective sanity check. They build trust among stakeholders, regulators, and ultimately the public. They provide the final layer of assurance that the functional safety framework established by the organization is robust, that it's being adhered to, and that the resulting system is indeed safe as claimed. They ensure that safety isn't just an aspiration, but something that is demonstrably proven, typically by individuals independent from the direct development team.
This has been a really comprehensive tour of ISO26262.2019 Part 8. It certainly highlighted the incredible depth and breadth of what supporting processes actually encompasses. It's far, far more than just background administration, which is maybe what I initially imagined.
Indeed. It covers a vast landscape. We've touched on everything from managing those complex customer-supplier relationships using development interface agreements, Clause 5, to meticulously specifying, characterizing, and managing safety requirements, Clause 6, to rigorous version control through configuration management, Clause 7, handling all changes systematically and analyzing their safety impact, Clause 8, ensuring everything is documented properly for accountability and traceability, Clause 10, making sure the software tools used are trustworthy through qualification, Clause 11, evaluating and qualifying pre-existing hardware elements, Clause 13, and software components, Clause 12, for reuse, and even leveraging extensive field data through the demanding proven-in-use argument, Clause 14. And we also cover those crucial Team B-specific clauses, 15 and 16, for interfacing with or integrating non-25262 systems in that specific industry context.
Listening to all that, it really does sound like these processes are the invisible glue, as you called it earlier, that holds the entire functional safety lifecycle together. They genuinely feel like the secret sauce to achieving demonstrable safety in these complex systems.
That's exactly it. They are the connective tissue. They link disparate development activities across different teams, suppliers, and lifecycle phases. They ensure consistency across that complex V-model product development lifecycle. And they provide that unbroken chain of traceability from the highest level safety goals defined for the vehicle all the way down to the implementation details in the smallest software function or hardware component.
And by providing this structure.
By providing this structured and rigorous framework for almost every aspect of development and management, these supporting processes fundamentally work to dramatically reduce the risk of systematic failures, the design errors, the process gaps, the human mistakes. They also establish the necessary controls and documentation framework needed to effectively manage random hardware failures. It really helps shift the whole approach to safety from being merely reactive, fixing problems after they occur, to being deeply proactive, building safety in and managing it throughout.
So they're definitely not just administrative burdens or bureaucratic hoops to jump through. They are actually the foundation for building assurance and confidence in the safety argument itself. It's about building trust, backed by evidence.
Precisely. They provide the essential framework, the procedures, and the documented evidence trail that guarantees robust functional safety. They build the confidence for the engineers, the managers, the assessors, the regulators, and the end users that a vehicle system is not just vaguely safe enough, but is demonstrably, consistently, and maintainably safe throughout its entire life cycle. It's truly about cultivating an organizational capability to build inherently safer systems, reliably and repeatedly. It goes far beyond just ticking boxes for compliance. It's about embedding safety thinking and safe practices into the core engineering culture, into the company's DNA.
That's a really powerful thought to leave our listeners with safety as part of the DNA. And perhaps one final provocative thought for them to mull over. As the automotive landscape continues its incredibly rapid evolution, with concepts like continuous over-the-air software updates becoming normal, AI-driven autonomous functions getting more complex, and interconnected vehicle ecosystems constantly expanding, how might the principles and practices of these foundational supporting processes, especially things like configuration management and change management, need to evolve? Will the existing frameworks described in Part 8 be sufficient, or will we need entirely new paradigms to manage functional safety in a world where the final product is potentially always changing and critical software updates might be delivered almost as frequently as new apps on our phones?
That is a fascinating and absolutely critical question for the future of automotive safety, isn't it? The very definition of a product lifecycle and final release is being fundamentally challenged by this new reality. How these supporting processes adapt will be key.
Indeed, it will. Thank you so much for guiding us through this deep dive into the essential supporting processes of ISO 26262 Part 8. We hope you, our listeners, feel more informed and perhaps just a little more amazed by the often unseen, complex web of activities that work together to help keep us safe on the road.